So I'm going to continue talking about a number of different inventions of mine. They're always open source. Take them, use them as you will. Um, you can read the details on the free blog. Just Google my name with the essay title and close their pop-ups. So this one is from the essay called Zipline Logistics. And the first thing I want to address is some limitations in materials science. When you're forming something out of clay, there are a few different problems that happen. One of them is that the clay, as you fire it into ceramics, will shrink. And that shrinkage depends upon the moisture level and the particle size. And you can never quite be sure how much it's going to shrink. It's always a question mark. Next is that during the firing process, there's a risk of fractures and even explosions within the kiln, depending on if the clay was stressed during the shaping process. And the third is that clay, even though it has a very high maximum strength, it's very brittle. So if there's any imperfections, it can shatter after forming ceramics. And it doesn't have a high strength of being pulled apart. Its tensile strength is low compared to something like steel. And steel responds by elastically expanding and then pulling back together. So these limitations of ceramics are why we don't have ceramic engines. We don't make engine blocks out of ceramic. And that's a pity because making engine blocks out of steel or aluminum means that we are not able to burn hydrogen gas in the engine. You can have a hydrogen fuel cell, which is a chemical reaction cell. It's very expensive materials that have to be mined destructively by basically slave labor and dictatorships. But just burning pure hydrogen gas in an engine, we can't do it because hydrogen gas will penetrate the lattice of the metal. And when it penetrates iron lattice, it gets between the iron atoms. The hydrogen gets between it and breaks the bond. And it's called hydrogen embrittlement because the steel engine block will actually crumble like dry feta. The crumbles turn into smaller crumbles. It's really gross. So you can't burn pure hydrogen gas in a steel engine block. It's just off limits. And hydrogen is a much better fuel than gasoline or diesel. It has a much larger expansion ratio. A small amount of hydrogen gas will expand when it burns, so the efficiency of the engine is higher. It has a much higher burn temperature, so it produces a bigger push. So you get a much more efficient, more powerful engine if you can burn hydrogen. But you can't burn hydrogen in a metal engine block. You could burn it in a ceramic engine block, but we have those problems with ceramic. So I addressed those problems with ceramic, which lets you make ceramic engines. And there's a number of benefits from a ceramic engine. It's not something that's intended to replace your diesel or gasoline engine. It would actually be for a different application space, but it would allow you to burn hydrogen gas. And hydrogen gas is very easy to produce from local biomass. If you're growing biomass to create biodiesel, then there's this whole expensive chemical process to convert the biomass into biodiesel, and there's a high loss rate. So converting biomass into biodiesel is not the best option. What you can do instead is take twigs and leaves and dry grass, straw, newspaper, old pallets, anything that would burn, and you put it in basically a steel drum or a clay jar and heat it. And during that heating process, it's going to release gases, and this is called wood gas from pyrolysis. And that wood gas has hydrogen gas. And so you can extract the hydrogen gas very simply and cheaply on your own farm from random debris. And then you can use that as a fuel source in a ceramic engine. And ceramic is just clay, so it's an abundant material. and the processing and kiln firing of ceramic is much less fuel and a much lower logistical cost for materials than making an engine block out of metal. So let's look at what we can do to make a ceramic engine so that we can burn local biofuels as hydrogen gas at high efficiency. First, I recommend the YouTube channel Fraser Builds, Fraser. He has a couple videos actually on alchemist's clay. This was a very old recipe where you boost the plasticity of the clay. It's not going to create microfractures while you're working the clay. And so it's much less likely to suffer damage during kiln firing. And it's a very simple process. You just take some starch, like from wheat, take some flour, and boil it. And the gluten in the starch is going to denature and chemically react, and it forms these long protein chains. And you mix that boiled starch into your clay body with your grog and whatever else. So that clay now has many times higher plasticity. The test that he shows is if you take the raw clay, make a worm out of it, try and wrap it around your finger, it starts to make cracks. Once you add this boiled starch, you can wrap it around your finger and there's no cracks. It's highly plastic. So it resists damage during the forming process. And you're going to have a much higher success rate. You have fewer losses in the what he doesn't do, which comes from some advanced research in material science, and I highly recommend, is adding carbon nanotubes. You add even just a few percentage of carbon nanotube, and you've multiplied the clay's fracture toughness, its resistance to shattering and fracturing, 6x. 6 times stronger against fracture. And the reason that happens is because the carbon fibers are laying all every which way in the clay body. And now if a fracture wants to form, it hits a carbon fiber, and the carbon fiber stops the fracture. And these are all short fibers. You don't need long carbon fibers. And you might think carbon fibers, this big expensive stuff. No, the only time carbon fiber is expensive is when you need the long fibers for like a sheet of laminate to make some expensive yacht or something. That's the expensive carbon fiber. You can make carbon fiber very cheaply if you're willing to accept that they're all small fibers. The easiest way to do that is to take straw or some other fibrous plant material and put it in a jug or a steel drum and heat it with embers to drive off the wood gas, which is exactly what we were doing to produce the hydrogen fuel. So while you're producing the hydrogen fuel with your plant matter, the charcoal left behind is going to be a high percentage carbon nanotubes. So you just mix the char in with your clay, and now it's 6 times the fracture resistance. Which means once you've finished making a bowl out of this carbon fiber clay, in the literature it's called ceramics matrix composite, you could hold it at 6 times the elevation and drop it before it shatters. So if I have a normal clay bowl, same clay body, and I've added carbon fiber to a different one, the height at which this one shatters when I drop it on a tile floor, I could lift this one 6 times higher before it shatters. So it's much stronger. So if you're adding boiled starch and charred grasses to your clay body, you've made far superior clay. And the carbon fiber helps to hold the clay body together. It's not going to explode if it's under pressure. And that's what you need for an engine block. So add your boiled starch, add your charred straw to the clay body with the grog. And now you're going to shape that clay body into cylinders, hollow cylinders and pistons. This is what you need for an engine, is a cylinder and a piston. And each of these, when you fire them, they're going to shrink different amounts. It's unavoidable. That's just how ceramics is. You can't get around that fact. But you can engineer around it by making one cylinder of one diameter and another cylinder that's also firing in the same kiln has a slightly smaller diameter. You made it a little bit smaller to begin with. And the next one is a little bit smaller, and the next one's a little bit smaller. Just ever so slight changes in diameters of those cylinders. Same with the pistons. When they've all fired, they've all shrunk by different amounts. Now it's just like batching socks. You just test to see which piston fits in which cylinder. And any that are left over, you're going to see if you can match them up with the next batch. So you've got some unmatched socks that are waiting for the next kiln batch to see if they can match. And maybe it takes a few batches before you finally match them up. But you will eventually match up almost all the pistons to almost all the cylinders. There's very little waste. And now you want to get a tight fitting. You don't want there to be gaps or wrinkles along that contact surface. And the easy way to do that is with glaze. You apply a thin slip of glaze to the inside of the cylinder and the outside of the piston, and you fire them again. This is just like normal ceramics. And when you've got those two glazes done, they're not going to fit perfectly, but you can mix some char and grit in a paste and grind them smooth. You can grind the glaze down and polish it so that you get a very tight fitting that's very smooth. So now you have a cylinder and a piston with a tight fitting, and it's smooth, and it's made out of ceramics and glaze. And that's what you can use to burn wood gas from pyrolysis of local debris. And it's going to be a much higher efficiency and a higher power rating than diesel or gasoline. So that sounds amazing, especially considering that the amount of energy you need to make the ceramic engine is much less than the amount of energy you need to make a metal engine. And you don't need as expensive tooling either. People in undeveloped regions could make their own ceramic engines. And metal is multiple times denser than ceramic, so you could have an engine of the same weight as a steel engine block with just thicker walls. And you multiply the thickness threefold, then its fracture resistance is multiplied by a polynomial increase. So you have a much stronger engine block at the same weight that was cheaper to produce without expensive tooling. And you can mass produce them for the processing of biofuels locally without expensive catalysts, without big factories or equipment, without advanced technology. So that's the ceramic engine. And now the other part of the SA zipline logistics is that you can make tiles which have cuts in them, and then you slide them into each other's cuts. And you can lay them out in grids on top of each other. And you glue those attachment points with low temperature pitch, or tar. You're just pouring tar in between as a glue. Tar is semi-elastic, so it's going to resist vibration and shock. It hardens up. It's easy to fix. So by making these hollow walled structures and stacking them as a big array like a honeycomb or a lattice, you can build up dimensionally thick walls which are made of just a few thin tiles in each location. So it's mostly empty, and you only used tiles and tar. So you can rapidly assemble a large structure that doesn't have a lot of mass, and it didn't require a lot of fuel or complex equipment to manufacture. The tar, by the way, is produced in the pyrolysis jugs, all the heavy oils in your material. When you're processing biofuels in a steel drum or a clay jug for pyrolysis gas, you're also going to leak out tar. So you're already collecting tar from the same process. So use the tar and the tile to construct tall towers with a hollow center. And these towers would be about 25 meters tall. And at that height, you can then have a fiber cable. You can make it out of flax and dip it in resin and coat it in pitch or tar. And so that fiber cable is going to be a zip line from the top of one tower down to the next tower. We're doing zip lines. And there's a second cable running in a loop inside the tower that is powered by your ceramic engine. So you take local debris, just farm waste or wood chips, whatever spare local debris you have, biofuels. You're processing it in your steel drums or ceramic jugs into pyrolysis gas. You're burning that in the ceramic engine to hoist on this cable packages. Big boxes, these are like crates weighing hundreds of pounds. The box goes up to the top, and then a little latch mechanism lets it slide down the zip line to the next tower. At the next tower, it gets lifted again and slides down the next zip line. And so the engines are each sitting at the base of their tower. The engine is not moving. You're not having to haul a vehicle when you're hauling material. You're not moving the engine or the fuel. You're just moving the package. And zip lines let you travel very fast, and it's not a lot of energy to lift it compared to how far it travels. It's only about twice as much energy in terms of joules per ton kilometer compared to the best railroads. So you're getting energy efficiency comparable to a railroad, but your fuel system is actually more efficient than a railroad because a train has to carry the fuel with it, and it's not burning that fuel as efficiently as a ceramic engine using hydrogen gas. And these towers are cheap to construct. And the towers can go, you can have one tall tower that goes to a second tower that's at an elevation, and then that tower goes up to another tower that's at an elevation. So you can climb elevations that railroads can't. And you can span gaps. If there's a chasm or a river, some obnoxious terrain, you skip over it. You don't need a railroad over that terrain. So this has more pathing options. It can travel across more diverse terrain than a rail car. And it's nearly as energy efficient using an engine that's actually more efficient in terms of the total system's efficiency. And it's a lot cheaper to construct without fancy tooling and equipment. You don't need fancy catalysts. You don't need fancy, expensive machinery. So these tile towers with the ceramic engines and fiber zip lines would allow you to build an entire zip line network across a continent faster and cheaper than your highway systems and your railroad systems. And one of the most valuable things about this is you don't need a driver. There's no one working by traveling with the package. There's no conductor, there's no truck driver along the way. Which means you're able to scale the volume of material that you're traveling. Your transportation volume goes way up without a limitation of how many people are willing to do that job. So if Eisenhower had made ceramic tile towers and ceramic engines for zipline logistics instead of the highway system, we would have a much denser network. You wouldn't be as far from a zipline, and it would be cheaper to get bulk goods to any location. Same thing for your high-speed rail today. I don't know why it's so important for you to go faster on a train when it would be better for the whole economy if you could go cheaper on a train that gets to more locations and it uses local biofuels without needing a massive refinery that explodes in some other state. So that's the basics of how you can use better engineering in industrial design and systems design to save a lot of time and effort and be able to scale out something that's more valuable for the entire economy. There are lots of places on Earth that currently don't have logistic networks because the value of the product that they want to transport and the volume of product was not enough to justify building a railroad or a highway. But it would be enough to build these towers. So they could benefit from this kind of logistics because they can cover diverse terrain. It's cheaper, and it's going to avoid the labor costs. There you go.